In this lecture, we will discuss a special type of data structure called cell arrays. Data structures in general help us store more than a single data type into a variable, and they also help us organize the data so that our source code is more manageable and also more readable. In MATLAB, regular vectors and matrices are restricted to store only a single data type, so you cannot mix and match different data types into a single matrix. For that, we are provided cell arrays where we can store different data types into a single variable. For instance, let's say we want to store the names and the grades of students in a class. We can construct a cell array where the first column contains the names of the students. Each entry will be a character array, and the second column could contain the grades of the students. There's another data structure called structures, which we will cover later, and these organize data into a group with each data entry having a field name. So taking the same example, we can represent each row as a separate structure. So let's say we have a variable A that will be a student, and then the name of the student will be stored as the name property of the variable A equals Ahmed, and the grade of this entry will be 100. So we have a single structure variable called A that contains two different properties, name and grade. You can create cell arrays much like you would create numerical vectors, except that whereas you would use square brackets for numerical vectors, you would use curly brackets for cell arrays. And another difference is that when you are creating numerical vectors, each element had to be a single number. On the other hand, when you create cell arrays, each entry is not restricted to be a single number. It could also be a whole vector, a matrix, or a string. In this example, we are creating a cell array that contains 4 elements, where the first element is a single number, the second element is a single character, the third element is a double array containing 5 elements, and the fourth element of the cell array is a character string containing 5 characters. You can use the cell plot function to display a graphical view of the cell array. Here the outermost box represents your cell array, and the contents of this cell array contains the individual elements, and these are single scalar values, vectors, or matrices. Let's see more examples of cell arrays. We already saw the first example where we created a row vector of cell elements. In the second example, we are creating a column vector of cells. Similar to numerical vectors, you would use semicolons to move on to the next row and get a column vector containing 4 rows. In the third example, we are creating a cell matrix with 2 rows and 2 columns. If you would like to create a cell matrix with each of its elements to be an empty vector, you would use the cell function with the number of rows and the number of columns you would like to create. Once you have created cell vectors or matrices, of course you would want to index them. There are 2 ways to index cell matrices. The first one is the parenthesis, and the second one is the curly brackets. You can think about cell matrices as a matrix of boxes, where each box can contain a certain number of elements. When you are using parentheses, you are selecting some of these boxes and generating a new cell array or matrix. When you use curly brackets, you would actually be opening up these boxes and extracting their contents out. Let's see some examples of these. In this example, we have a cell vector with 2 cells. Both cells contain a vector with 2 elements. Now, when we say A parenthesis 1, we are selecting the first cell and generating a new cell. So we are not really extracting the contents of the first cell. We are simply generating a new cell array using the indexed elements. In this case, there's only one cell being indexed. In the second example, we have a curly brackets one. Again, we are referring to the same cell as before, but now we are actually extracting its contents. So the contents will be taken out. If the contents is not a cell array, then the result will not be a cell array. In this case, the result is a vector with two numbers. There's a function in MATLAB called isCell that will return true if the argument that you provide to it is a cell. So in this example, a parenthesis 1 will result in true because it is a cell, whereas a curly brackets 1, which is the contents of the first cell, it's a vector, it is not a cell, so the result of this cell function call will be false. Let's see more examples. Here I'm creating a cell matrix with 2 columns and 2 rows. In the first cell I have the character A. In the first row, second column, I have a vector that contains numbers 5 and 6. In the second row, first column, I have another vector that contains numbers 7 and 8. And finally, in the last cell, I have a string, which is a character array that contains the word hello. Now, I'm indexing the first row, second column. And because I'm using curly brackets, the result will be the contents of that cell. In this case, it will be a vector that contains numbers 5 and 6. In the second example, we are indexing the first row, but the first 2 columns. And because curly brackets is being used for indexing, the contents of those cells will be taken out. So because we have multiple boxes, multiple cells, when we extract their contents, that results in multiple answers, each answer being the contents of the corresponding box. So we will have an answer that contains A and another answer that contains the vector 5, 6. This is quite similar to a function returning more than one output argument. And similar to the way that we capture multiple output arguments from functions, we can capture multiple answers that are extracted from a cell array using a vector notation on the left-hand side of an equal sign, and on the right-hand side we would have the expression that extracts the contents of a cell. So again, we will be extracting the letter A and the vector 5 and 6. The first one will be stored in X, and the second cell contents will be stored in the variable Y. When you chain indexes, you simply evaluate them from left to right. So here I am first referring to M curly brackets 3. Remember that MATLAB uses column-wise storage. So M3 would refer to the second row, first column, which will be the vector 5, 6. And then within that vector, I'm referring to the second element of it, which will give me 6. So the result of this will be number 6. In the next example, I'm referring to the first 2 elements of this cell matrix. Again, we are using column-wise storage. So the first 2 elements would be the letter A and the vector 7 and 8. When MATLAB displays this result, it will display a summary. That's why we do not see the contents of this vector, but only the fact that it's a vector that contains 2 numbers. If you would like to display the contents of all the cells, you can use the celldisp function and provide a cell matrix to it, and it will print out each of the cells individually. The AND keyword works very similar to the way it does in vectors. Here I again have a 2 by 2 cell matrix. When I'm performing linear indexing, the AND keyword will be replaced with the number of elements in the matrix, In this case, I have 4 elements, so this is the same as saying m parenthesis 4, and I'm using parentheses, not curly brackets, which means I will be getting a new cell array as a result, and that cell array will contain a single cell, which will be the last cell in this cell matrix, and that will contain the word hello. In the next example, I am indexing the first row and the last column. When the AND keyword is on the right-hand side of a comma, it will be replaced with the number of columns. So this is the same as saying M1, comma 2. And because I'm using parentheses, I will be getting a new cell array that contains a single cell, and that cell contains a vector of numbers 5, 6. So the result will be a cell, a single cell, that contains a vector which contains numbers 5 and 6. In the next example, I am again referring to the last box, the last cell. So the AND keyword is replaced with number 4, M curly bracket 4. Since I am using curly brackets, I will be extracting the contents of the 4th cell, and that will give me a character array, not a cell, a character array, which is a vector of characters containing the word hello. The last example shows how I can chain different indexes. Again, M curly brackets AND will give me the word hello, and in that vector I'm indexing the second element of it. The second character will be character E, so I will get a single character E. To remove elements from a cell array, you must use matrix indexing, meaning you must use parentheses, not curly brackets. In this example, I am referring to the first row and all columns, so the first row of matrix M and the first 2 columns of matrix M, and I'm removing it by assigning it to an empty vector. And as a result, the cell matrix M will become a cell array that contains only 2 elements, which will contain the values 7, 8 in the first cell and hello in the second cell. One of the most common uses of cell matrices is to store strings in them. Let's first see how we can work with strings using regular matrices. The character function, if you provide it with multiple strings, it will generate a character matrix where each word will be padded with spaces as necessary. Let's see how this works in MATLAB. So let's create a character matrix using these names. And you can see in the workspace window that this variable has 3 rows and 8 characters. Even though the first name Mike is only 4 characters, MATLAB will pad it with additional spaces so that you have a proper matrix. We can take this character matrix and convert it to a cell of strings using the cell str function and providing it the character matrix. This will remove the additional spaces at the end of each line, and you will obtain a cell array with 3 items in it. The function isCellStr will tell you whether a variable is a cell string or not. So in this case, S is a character matrix. The function isCellStr will return false. Whereas isCellStr T is a cell array and all of the elements are strings. This will return true. We can take a cell array of strings and convert it back to a character matrix using the character function again. And again, each word will be padded with spaces so you have a proper matrix. Another important use of cell arrays is to capture a variable number of input arguments in functions. Here we have a function called smallest that takes a number of input arguments and returns the smallest one. We have a named argument x, and everything else provided to this function will be captured in the special variable named varargin, and that stands for variable input arguments. Varargin is a cell array if, when this function is called, only a single input is provided, it will be copied into X and varargin would remain empty. If this function is called with two input arguments, the first one will be copied into X and the second one will be copied into the varargin's first cell. We can take varargin and write a for loop to iterate over its elements to find the smallest one. In this example, we are initializing the output variable y to the input variable x and iterating over the varargins provided to this function. And for each one, we test whether it is smaller than the value of y that we have seen so far. And if so, we update the value of y to become the new smallest value. And after we have finished covering all of the varargins, the variable y will contain the smallest input provided to this function. There's another special variable named nargin, whose value will be the number of inputs provided to this function, which will be equal to the number of elements in varargin plus the number of any named arguments that you have in this function. On the right, we see some example calls to this function. In the first example, we have provided 5 and 3. 5 will be copied into the x variable in the smallest function, and the number 3 will be copied into the varargin, where varargin will be a cell array containing a single value 3. And as a result of this function call, nargin will be printed as 2, and the answer, which will be the smallest of all of the inputs calculated by this function, will be 3. In the next function call, we have provided 5, which will be copied into x again, and the rest of the input arguments, 3, 2, and 10, will be copied into the cell array nargin, and the function will find the smallest of them, which will be 2, and nargin, which is the number of input arguments provided to this function, will have a value 4, which will be printed at the end of our function. An alternative to using varargin is to use the exist function to check for existence of input arguments. So here we have a foo1 function that takes a and b as inputs and returns their sum, product, and ratio as outputs. In foo2, what we have is that if the variable b does not exist, it's initialized to 3, and if the variable a does not exist, it is set to 2. In this manner, we are providing default values for the input variables a and b. Whenever they are provided, the provided values will be used, and whenever they are not provided, these default values will be used. Let's see them in use. If we call the function foo2 with a single input argument 2, which will be copied into a, and then b will not exist, so this if statement will be active, and the value of b will become 3. The next line of code will be skipped since a already exists, and the function will calculate the sum, the product, and the ratio of a and b. Since we are not capturing all of the returned arguments, only the first one will be printed in MATLAB, which is the sum equals 5. In the second function call, we are providing both a and b. 2 will be copied into a, 4 will be copied into 4, and the body of these if statements will be skipped since the conditions are not met because we have b and a existing. And then we find a sum, which is 6. In the last example, we have foo2 function call without any input arguments. So we are not providing a or b. When we don't provide a or b, the bodies of these if statements will be executed. B will be set to 3, a will be set to 2, the sum of them will be 5. On the right, we accomplish the same functionality using varargin variable. If the length of the varargin or the number of elements in varargin is less than 1, it means no inputs have been provided to this function. If so, we set the first element of the varargin to become 2. This is equivalent to setting the value of a to become 2. Since this function foo3 does not have any named input arguments, everything will be captured in varargin. So using the value of nargin is the same as using length of varargin. If less than 2 inputs have been provided to this function, that means the second input has not been provided. And if so, we set the second element of this cell array, of this varargin variable, to become 3. And this is equivalent to setting b equals 3 in the previous example. And then once we finish up setting the defaults, we take the varargin 1, store it in A. We take the second element of varargin and store it in B, and calculate the sum, multiplication, and division. Since these function calls do not capture all of the returned arguments, MATLAB will again print only the first one, which is the summation. So here we call with a single input argument, we get 5. With 2 input arguments, in which case varargin will be a cell array containing the values 2 and 4, which will be copied into A and B. And then we again find the sum to be 6. In the last one, we are not providing any input arguments. Varargin will be an empty cell array. And then we will be filling in with our default values, 2 and 3. And then 2 will be copied into A, 3 will be copied into B, and the summation will be calculated as 5. If MATLAB has support for variable number of input arguments, does it also have support for variable number of output arguments? The answer is yes. The answer is yes. And the special variable names involved are varargout, which stands for variable number of output arguments, and nargout, which is the number of requested output arguments from this function. So here we have the varargout cell array. We store the multiplication in the first element and the division in the second element. This is not of much use. We might as well return m and d as the returned arguments. When you call this function and do not capture the output arguments, MATLAB will implicitly capture only the first output argument, which is s. And even though you are calculating the product and the ratio variables and storing them in the output argument, MATLAB is not really storing them in the command window. To capture them, you would use the vector notation, and we capture A, B, C from the function outputs. Now, the most important usage of using variable number of output arguments is to improve the performance of your function, such that if an output argument is not requested, you might as well not calculate it. So you should only be calculating the product if it is being captured by the function call. There is an important distinction between nargout and nargin. Remember that nargin contained the number of input arguments provided to a function, and that contained the number of named arguments plus those captured as part of the varargin. On the other hand, nargout contains only the number of variable output arguments, excluding the named output arguments. So here S will not be counted toward nargout, and only the output arguments captured after this variable S will be counted toward nargout. So if you are capturing 2 output arguments, S and M, then nargout will be 1. So let's get back to this function. If nargout is greater than 1, which means the first variable output argument is being requested, we calculate the product and store it in the first element of the varargout cell array. And if a second variable output argument is requested, we calculate the ratio and store it as the second entry of the varargout cell array. And from the caller's perspective, the outputs of these function calls will be identical. But foo3 will be slightly faster because it avoids redundant calculations when the multiplication and the ratio are not requested.